entry and exit procedures to avoid incidents like the one I just told you.
Are not the only way transmission can occur. Dermatitis or other
It never
skin
occurred to me
lesions
that a few
provide
quarts of oil could contribute to the pollution of our environment.
Great training session. The one thing that we tried to
have to change an auto head. Go through the shutdown.
Hey, Tony, can you hold up for a minute?
Sure, Scott. What's up?
I got a problem. I've got to get all these orders out, and the packing line keeps coming down.
Again?
Same old problem.
Okay, you give me a half hour, I'll lock out, and I'll fix it.
I don't have a half an hour. If the line is down for 30 minutes, I'm going to miss the shipment.
Can you give me 5 minutes?
Yeah.
Okay, I'll tell you what. You make sure the start-stop switch is off. I'll have you online in 5 minutes. It's a deal.
Although we know that electricity will readily pass through the human body, often with severe or even fatal consequences, accidents like this continue to happen. Because electricity is such an integral part of our daily lives, we tend to become complacent and often don't give electricity the respect it deserves. A single mental lapse or the bypassing of even one electrical safe work practice can produce another victim in a flash. You see, electricity presents a special kind of unseen danger. In this presentation, we'll examine the effect of electricity on the human body, discuss some of the simple procedures that can be followed to avoid electrical accidents, and learn what action should be taken if you are present when one occurs. You may never have thought about it in precisely these terms, but the human body is really an electrically controlled machine. Our nerves transmit electrical control messages throughout our body. These signals are used to think and to control our muscles and internal organs, including the respiratory system and heart. The internally generated power level of these control signals is very low, thousands of times lower than that used to power the electrical equipment with which we are all familiar. However, if a sufficient quantity of this external electrical power is allowed to flow through our bodies, it quickly overwhelms the normal control signals of our nerves and can cause injury, or even death. So the most important principle of electrical safety is to prevent your body from becoming part of an electrical pathway, also called a circuit. To fully grasp this electrical circuit concept, we should understand another electrical term, conductor. As you know, electricity flows through wires and cables, usually made of copper or aluminum. Materials such as this cable that easily permit the flow of electricity are called conductors. Most metals are conductors, but some are better conductors than others because they have less resistance to the flow of current. Most liquids and the earth itself are also conductors. Other materials resist the flow of electricity so strongly that they can be used as protection against electrical contact. These are called insulators and include dry wood, most plastics and ceramics, rubber, and glass. Every electrical device must be connected to at least two conductors. One can be thought of as leading in from the source, the other as a return pathway. The current flows in one or more conductive loops called electrical circuits. Electricity begins at the source of power, flows along a conductive pathway to the electric device, gives up the energy required to provide power, and then returns to its source to complete a continuous circuit. If a human body accidentally comes in contact with a live wire or component, the electricity will similarly try to flow through the body and back to its source. For the circuit to be completed, the current must also have a means of exit through a second conductor. Otherwise, it will not be completed and no injury will occur. The problem is that we are almost always touching a second conductor, the Earth. Electricity can flow back through the ground to its source. Thus, we usually have to touch only one energized conductor to become part of a completed circuit. The body is not an especially good conductor. When the skin is dry and functions as an insulator, it resists the flow of current to a limited degree. But this resistance can be overcome if the electricity has sufficient force, and it usually does. This electrical force is called voltage and is measured in volts. It can be thought of as the pressure of the electricity as it attempts to return to its source. If you are wet, as little as 12 to 24 volts may force its way through your body. If you're completely dry, it may take 50 volts or even more. But normal house current is 110 to 120 volts, and industrial equipment commonly uses 220, 440 volts or more. So there is almost always enough voltage present to cause damage if the pathway is completed. The term amperage is used to express the quantity of current flowing in a circuit. It is the amperage that is the most destructive factor in an electrical accident. We will experience a tingling effect at only 1/1000th of an ampere. At about 5/1000th, we will begin to feel pain, and at about 31,000th of an ampere, the current begins to overwhelm the nerve signals in our bodies. This level of exposure will quickly cause serious, even fatal, effects. The greater the amperage, the shorter the period of exposure necessary to cause bodily harm. Electrical circuit breakers are designed to detect and stop excessive current flows. However, typical breakers do not trip until 15 amperes or more have flowed for 1/4 of a second or longer. This exceeds our body's safety margin by a factor of several hundred. Clearly, circuit breakers cannot be depended upon to provide personal protection, nor are they intended to do so. Their primary purpose is to prevent damage to equipment. Ground fault interrupters, or GFIs, on the other hand, are designed primarily to protect people, but only under special circumstances. In the event of a short circuit, they can shut down power fast enough and at low enough amperages to provide protection. They are excellent safety devices and should be used whenever possible, but even they do not provide total protection. The only real protection is to prevent contact with energized conductors or parts. With this background in mind, let's examine the primary forms of electrical injury and their effect on the human body. They can be subdivided into 3 categories: electric shock, flash burn, and fire and explosion. Shock effects can range from a minor irritation to cardiac arrest. The most common symptoms of electrical shock are muscular control failure or contraction. This often causes the victim to grasp and be unable to release the source of the shock. Muscular contractions can also lead to other problems, such as falling from an elevated work position. Respiratory failure, heart fibrillation, that is the cessation of the rhythmic pumping action of the heart, and severe surface or deep internal tissue burns from the heat generated by the current flow. To place this tissue burning capability in perspective, human tissue is destroyed at only 120 degrees Fahrenheit, and brain tissue damage occurs at less than 110 degrees Fahrenheit. Even a contact as brief as 1 second with a standard 120-volt, 15-ampere circuit can generate enough heat to destroy the tissues of a human finger. Another important factor related to electrical shock injury is the specific path of the current through the body from conductor to conductor. For example, a hand-to-hand pathway would be especially dangerous because it passes through the heart, while a right hand to right foot path, as illustrated here, would be less likely to cause heart fibrillation, as most of the electrical energy would not pass through the heart. Skin condition is another variable. The human body becomes a better conductor when skin resistance is lowered as a result of being damp from sweat or rain. Remember, because electricity cannot be seen and the effect of a shock is dependent upon so many factors, no shock can be considered as harmless. The second major source of electrical injury is flash burn from uncontained arcing. Under certain circumstances, for example, when extremely high voltages are involved, the insulating ability of air can be overcome and electricity will jump from one point to another. This is called arcing. Lightning is a natural form of arcing. An electrical arc generates hot ionized gases, which, if not contained, are capable of causing serious flash burns of the body and ultraviolet ray injuries of the eyes and skin. If you work where arcing is a possibility, wear flash and flame-resistant clothing, as well as face protection. Protective equipment has saved countless lives. In addition to flash injuries and burns, electrical arcing can also be a source of ignition. This brings us to the third major source of electrical injury, fire and explosion. Ignition of combustible vapor or dust can be caused by electrical arcing, sparking, or a variety of other sources, some of which you may not expect. Many electric motors, including those used to drive battery-powered screwdrivers and drills, produce continuous internal arcing during normal operation. Relays, switches, actuators, distributors, and other devices produce sparks each time they function. Even tiny electrical sparks from sources such as the switching of a battery-powered flashlight or the bell of a telephone can be enough to trigger an explosion and fire if flammable vapors are present in the proper mixture. For this reason, pneumatic or hydraulic-powered equipment or non-sparking hand tools should be used whenever there is any possibility that flammable vapors may be present. We've spent some time considering the three major sources of electrical injuries: shock, flash burn, and fire and explosion. Next, we'll examine the situations where accidents are most likely to take place and identify the related safe work practices necessary to prevent their occurrence. These accident situations can be subdivided into four major categories: those involving accidental contact with an exposed conductor, situations where the hazard cannot be seen, working in wet conditions, and bypassing of safety procedures. The first of these, accidental contact with an exposed power source, is the largest single cause of electrical injury. Any conductive object, vehicle, or piece of equipment, from a metal rod to a piece of jewelry, can become part of an electrical path as a result of inadvertent contact with a power line or any other source of electricity. If you touch an energized conductive object, either directly or with something you may be carrying, such as a conductive tool, the result can be lethal. Barriers and warning signs on electrical equipment are in place for your protection. Ignoring them increases the possibility of injury. The chance of inadvertent contact can be reduced by the use of protective equipment, such as properly rated and tested insulating gloves and non-conductive hard hats. If protective equipment is called for, use it every time. The key to preventing accidental contact is to be alert to your surroundings. Don't get yourself into a situation where you or any object you are touching can contact or even come close to an energized conductor. Be especially cautious if you encounter conditions where it is necessary to place your hands or tools in a position that is difficult to observe. Do so only if all sources of power are locked out. Even when this has been accomplished, take whatever other actions are available to improve your vision. Remove covers, use portable lights, or even mirrors to obtain a clear view of your work. Soil or pavement can also obscure vision. The possibility of striking a buried power line is another unseen hazard. Don't break ground unless you have obtained the necessary permits and the location of any buried lines has been clearly marked by the proper authorities. The next category of accident situations we'll consider are those involving working in wet or even damp conditions without the proper equipment. Water and many other liquids are conductors, so extra precautions must be taken when electrical equipment is used in a wet environment. First, use only equipment that is specifically designed and rated for use near water or other conductive liquids. Be particularly careful to follow all recommended grounding and bonding procedures. Wear tested and inspected insulating gloves and boots rated to provide adequate protection. Whenever possible, connect your equipment to a ground fault interrupter. As we've already seen, this extremely sensitive device provides some degree of protection. The fourth and final category is unsafe situations that occur when safety procedures are ignored or intentionally bypassed. For example, working on equipment that has not been correctly de-energized, locked, and tagged out. The rule to follow here is de-energize and lock out every time. Don't work on electrical equipment unless every source of energy has been neutralized, locked out to prevent inadvertent startup, and tested to ensure that the de-energizing process has been completely effective. Taking a shortcut, such as using an on-off control to de-energize a machine before making a quick repair, can be disastrous. There is always the possibility that it will be restarted by an automatic timing device or by someone who doesn't realize you're there. Removing the ground connection on a plug as a convenience is another dangerous practice because it significantly increases the risk of electrical shock. One of the most common misconceptions about electrical safety is that regarding safety provided by grounding. It is not foolproof. Current returns to its source through every conductive material available. While most will be dissipated through ground, some will also follow other pathways. Portable equipment should be inspected before each use to ensure that the ground connection is in place, the power cord is in good condition, and the equipment is free of any potentially hazardous conditions or defects. When an extension cord is required for portable equipment to be used at a distance from its source of electricity, it should be carefully positioned to prevent accidental damage and properly sized to carry the required amperage. Extension cords are intended for temporary use only. Another electrical safety measure that is often overlooked involves the use of undersized conductors and the overloading of circuits. Both of these conditions can cause overheating and ultimately result in fire. Whenever possible, open or close circuits with the panel door closed, using external handles or relay controls. If it is necessary to open it to reset a circuit breaker, stand to one side to minimize the possibility of an arcing injury. Protective clothing should be worn when the voltage or amperage is high, especially if the circuits include electric motors or transformers. If a fuse or circuit breaker blows or opens, restore power only after identifying and eliminating the overload or other problem that caused the safety device to operate. When a blown fuse must be changed, be sure the replacement has the correct rating. Replacing a fuse with one of a higher rating defeats its purpose as a protective device and can create a serious fire hazard. We've spent the last few minutes discussing the situations where electrical accidents are most likely to occur and the respective protective measures for each. Now, let's consider the action to take if you are present at the scene of an electrical accident. If a coworker is the victim of an electrical shock, your first actions should be to protect yourself, call for help, warn others of the hazard, and shut off the power if possible. If you can't do it, call for someone else to do so immediately. As we said earlier, electrical shock disrupts muscular control, and the affected individual may be unable to free himself from the point of contact with the conductor. If this occurs, and it is impossible to de-energize the circuit, the victim may be pried or knocked free with a non-conductive object, such as a broom or dry board. Always protect yourself first. Never attempt to pull the shocked individual away from the energized conductor by hand. You could become a second victim. Call for medical assistance as soon as possible. In the event of respiratory paralysis or heart fibrillation, administer CPR, but only if you are trained to do so. There is also the possibility of encountering a fire in or around electrical equipment. Should this occur, protect yourself, notify the proper authorities immediately, and warn others to leave the area. If you are trained and authorized to extinguish the blaze and can do so without the risk of personal injury, use only dry powder or gas extinguishers. Water and other liquid extinguishing agents conduct electricity and consequently can present an additional hazard. Electricity is an essential element in all aspects of modern life. The ability to harness and use the awesome power of electrical energy is the foundation of modern industry. But because we are unable to see it, electricity presents a special kind of danger. It must be treated with the utmost respect. Be alert to your surroundings. Avoid any situation where your body could become a pathway for electricity. Follow recommended de-energizing procedures. Lock out and tag out the circuit and prove that it is de-energized before starting work. Plan your work carefully, with safety as the #1 consideration. Give electricity the respect it deserves. Don't discover that a circuit is live or hardened.